All right. Good morning, everybody. Happy Monday. Um, so, I guess first announcements. So, I will update the assignment to deadline to be due on Wednesday before midnight. I think that's a fair amount of time to give. I don't really think. I mean, the assignment, this one can be, challenging to work on, of course, but I don't really see this as being something that takes it's not as a big project like the first assignment was, so I think a few days extra would be fair. So I guess to Wednesday, I'll have it sort of due by then. So probably at some point this week, I'm hoping to get through the last few sorting algorithms, and then I'll be able to give out our third assignment, which will be just a written assignment to just sort of trace out the sorting algorithms and plus some other math type stuff like this big notation math type stuff I'll have on there. So definitely not as intimidating because it's not a coding assignment. So anyway, that's going to be sort of the path for right now. But anyway, I guess let's go back to the to OneNote and just go ahead and sort of recap from last week and continue with the new material. So let's start a screen share. So um, last week we went over our first sorting algorithm, insert and sort. Nothing really too fancy about it. So remember this strategy, we always had the element right after that green part. We had to basically in our inner loop shift elements over to the right to make room for our new key to be inserted. We do it kind of one by one until eventually we have a sorted list. So until this whole entire list is one big green box, then obviously it's a sorted list. So that's pretty much how it worked. So in the worst and average case, it would be n squared runtime because inner loop would have to run a either n times or a fraction of n times, but this summation here models the worst case scenario. And on average, it'll also relatively have to, the inner loop will have to run several times for every outer loop iteration. So it's going to be mostly quadratic in runtime. So in the average and worst case, it's quadratic. But we have these scenarios where it can be good, where it can be O of n if it's sorted, or if you have an arrangement like this where we notice that every single time we run search and sort the outer loop, the inner loop will always run at most k number of times, which is in this case k is 3 in this example. But every single time you run the inner loop, it will run at most k times every single time. So then the runtime will be k times n or O of n. As long as k is something relatively small, it's not a factor of n in any kind of way, just some constant that's very small, it will be O of n. So um, insert and sort is sort of the most preferred quadratic sorting algorithm because it has these good scenarios. Because selection sort, which I could try to talk about that maybe at the end when I finish up all of our sorting algorithms, is also n squared, and there really isn't a scenario where it can be better. Bubble sort could have a case where if you update bubble sort, you modify the code a little bit, you actually can get O of n if you have this flag sort of portion. You have this flag sort of code where you just sort of check if no swaps were done in one pass, then you know it has to be sorted. But you have to do modifications to it, whereas a search and sort without any modifications will be linear in runtime in several scenarios, or at least in these two scenarios, which sorted or when you have a small size k like this, where the inner loop portion runs a k number of times. So that's the idea. But overall, though, insert and sort is O of n squared because the best case scenario is not very common, or you can kind of have wishful thinking and hope that happens, but typically the average case will happen where the list is kind of randomized and the inner loop portion will have to run several times every single time, which will definitely give us that sort of quadratic bound, basically. So insert and sort is definitely O of n squared, but it has some scenarios occasionally where it can be better. So that's sort of the conclusion um, on insert and sort. So now let's go over our next sorting algorithm. So this next one's going to be merge sort. All right. So merge sort is going to be a divide and conquer algorithm. Let's go ahead and first write that out. I'll kind of explain what this is. What does it mean to be divide and conquer? Let's try to spell it correctly. So I believe it's spelled like this: divide and conquer algorithm. Okay. So, I mean, I guess divide and conquer comes from the ancient Romans when they would, I guess, when their army was smaller than the enemy army, they would typically take their whole army and always attack a small portion of the enemy army. So maybe even though the overall enemy army was larger, but every single battle they had a larger number in that small battle. So they would sort of in small increments sort of be able to take out the enemy army. Now, I guess I would need a different example to sort of show divide and conquer. So divide and conquer can be thought of as like, so for example, Audi cars. So of course the car factory that sort of assembles Audis. Now of course you could in one sort of one factory sort of build all the components of the Audis and assemble them together in that one place. But what I've noticed, what Audi does, or most car manufacturers do, so for Audi, let's say the let me see the engine might be built in a factory in Austria, and then when they have their let's say the transmission, maybe they build that in Hungary, and a fuel injector, maybe they build that in Slovakia, and at the end they send those components out, and then they had a final assembly point somewhere in Germany. I'm guessing either in, I think probably Munich or something. So the idea is that instead of having one car factory assemble all the parts and then assemble the final product together, they have several other smaller factories around Europe that sort of create each individual component of the car and they send it out once they're done. And there's a final assembly point where you put all the parts together to create the car. Or it's kind of like think of divide and conquer like a big software project. You have several teams of programmers. One team does like the front end, one does the back end, one does the designs, especially for a game development. They have like the designs of the game and so forth. And at the end, they combine all the code into one project. So divide and conquer is basically that. You take the problem and sort of put it into small components, and then at the end you put them together. It doesn't matter what order you sort of in what order the components are done. As long as they're all done at some point, you can assemble them together. So like the Audi car plant, as long as all the parts are there, you can do a final assembly. So let's say, for example, if a transmission gets there first, and then we have the engine, and then we have the fuel injector, it's okay. As long as they all get there, we can assemble it at the very end. That's divide and conquer. So let's go ahead and apply this divide and conquer type paradigm onto merge sort. So divide and conquer is a class of algorithms, and for merge sort, divide and conquer does the following sort of action. We're going to first break the list. So we're going to sort a list of elements. We break the list into two pieces of equal, or you can say almost equal length. So for example, if you have an odd number of elements and you try to break it into two equal pieces, well, it's impossible because if you have 7 elements, you'll have one sort of piece will have 3 elements, one will have 4. But that's just about equal. So you have one element more on one list. That's going to be good enough. So that's the idea. Break it into two equal or almost equal sort of sizes. And then we simply call merge sort on each piece. So obviously, this will be done recursively. I think I messed this up recursively. So the idea is that, yes, it'll be recursive, so I know everyone's favorite is recursion. And of course, how's recursion work? Well, of course, it's magic, and yes, we have an agreement here. So it's magic recursion. There's nothing to recursion that makes any sense at all. It doesn't, I mean, it's not really known how it works. We just know that it's this mysterious kind of function that just works. So when we call merge sort on each piece, what's going to happen is it's going to basically sort of, how shall we say, it's going to get two sorted lists. So let's go ahead and just write this out. So we have our initial list given to us. So we're given a list of size n. And then we're going to have our one piece. It's going to, so we're going to have a list. So we're going to call merge sort. So call merge sort on list sort of one, and then call list or call merge sort on list two. List one will be that first half of that list. List two will be that second half. So you break it into two even pieces, and then the result is we're going to get, so it returns a sorted list. And of course, it will do it magically. So we break it in two pieces, we call a merge sort on each piece, and magically we will have two sorted lists. Awesome. And once we have that, we're going to merge. We're going to merge the two sorted sublists to obtain one sorted list. And that's basically it. That really is merge sort. So the only really hard part of merge sort is the merge operation. So basically, we're going to have to merge two sorted lists many times throughout the execution of merge sort. So let's first go over how does merge actually work. Well, let's start with that. That's sort of our first step for merge sort. So I'm going to, let's see, I'm going to make a shape. So let's just, yeah, this will be nice. Let's go ahead and create these two lists over here. And I'll make another shape as well. I can probably just copy this, I'm guessing. Let's see. Okay. Cool. So those will be two arrays. I'll make just one large array at the very end. All right. So basically, so let's say I want to have maybe a 4-element list over here, and another 4-element list over here. Yep. Then I'll have an 8-element list over here. Like that. So basically, when we call merge sort, we're going to first have these two sublists. So let's say we'll have 3, 5, 6, and 7, 1, 2, 4, and 8. So we have these two sublists, and they're definitely sorted. So I want to merge these two into this bigger list at the bottom. So to do this, I'm going to first create a couple of, I guess, counters. So we're going to have our blue counter here, a red counter there, and then I guess a green counter below. So all we're going to do is just the following sort of work. So we're going to first compare the element in the blue counter with the red counter and sort of pick the smaller element. So right here we can definitely see that 1 is smaller. So we're going to write 1 into the first element of this larger array. Then we're going to move the red counter over by 1. And likewise, the green counter also moves over by 1. Now, since what happens is we stop once the blue and red go beyond their respective arrays, then we're done. So right now we can see that we're not past our 2 arrays, so we're going to have to keep working here. So we go ahead and compare the element in the blue counter with the element in the red position. And we see here the red element is smaller, so we're going to write that red element over here. And we're going to move this counter over by 1, and move this counter, green counter, over by 1 as well. And again, we do the same exact process. We check, well, which one is smaller? Well, the blue counter element 3 is a smaller element now, so write that 3 into this array, and then move the blue counter this time around. And the green counter, again, well, we just move that regardless. Let me check once again, the blue or red. Well, the red element contains 4, which is smaller, so write the 4 into this larger array. Let me move this over by 1, and move this over by 1 as well, like that. And then we're going to, again, compare. So it looks like the blue element is smaller, so write that blue element 5 into this array, move this counter over by 1, and move the green counter over by 1 as well. And again, we compare. Looks like the blue counter is smaller because it contains 6, and a red element contains 8. So go ahead and write the 6 into the green position. Move this over by 1. Move this one over by 1 as well. Again, we have to compare because we're not really done yet. So the blue element is again smaller. So you write that into this element. Move the blue counter over by 1, and the green goes over by 1. Now, once you have a condition where one of our counters is already beyond, then we simply have to copy everything in the other array until that counter gets to the end. Now, in this case, however, there's only one element left to copy, so you just go ahead and copy the element over here. And then this red counter goes beyond, and so does the green counter, which means we know we are done. Now, potentially, if let's say everything in that right array was larger than left array, then what would happen is all the left array elements would have gone copied in, and then it would have hit that blue counter would go beyond that array's bounds, and then we would just go ahead and just copy everything from the red from that second array over just like that. If let's say, for example, if you would have had 1, 2, 3, 4 in our first array, and then 5, 6, 7, 8 in our second array, then what would have happened is the blue counter would have kept on moving because every time you compare, that blue element would have been smaller. It would have gone past its respective array bounds, and then the second array, we would just go ahead and just copy everything over into that bigger array. So anyway, that is sort of how we perform this merge operation. So all merge does is takes 2 sorted subarrays, and it will combine them to make a larger array that's sorted. So that's all merge actually is. I don't know why. This is actually the non-recursive part. This is sort of that conquer part where we first had to recursively get the 2 subarrays sorted using merge sort, and then we have to merge them to create a bigger sorted array. This part actually would not be the recursive part. Yep. Well, if there's the same, then we just pick one. Then it's really arbitrary which one we want to use. So it doesn't matter which one we pick, but we can assign that just the left element, the left array, or the first array can be used. But there's really it's arbitrary if we do that. We can just arbitrarily pick one of them and assign that into the bigger array. Yep. So that's all merge is, and it's actually, let's first look at the runtime for merge. So what's the runtime for doing merge over here? Well, let me see. We have 4 elements in this array, 4 elements in that array, so we had 8 elements in total. We did actually 8 steps to merge them. So if I'm going to go ahead and go on a limb here and say that the merge operation, merge takes O of n time. It's relatively a pretty fast operation. I mean, I don't know why merging is so complicated in traffic. When a merge happens in traffic, why it's always so terrible. Well, there's other reasons as to why that happens. I'm not going to go all political here and say why, but for right now, we'll just say that for some reason in traffic, merge is a very complicated operation. But this is really just a very simple linear runtime to merge two sorted lists. Yes, this works if the two arrays are both sorted, but luckily, if you look at our code of merge sort, our pseudocode, if you will, we first call merge sort on the left list, then the right list, and it returns back magically two sorted lists, and then we just go ahead and merge those two sorted lists. So we always call merge sort first on on the first half of the list and second half of the list. It returns back two sorted arrays magically, and then we merge them because we know merge sort works. We have to make ourselves believe it's going to work. And since it works, we know we'll have two sorted subarrays, so we can simply merge them to make a bigger array. And no, it works in any length. I mean, it doesn't have to be on even or odd. I'll do an example, in fact, today that I'll pick like not a power of 2 just to see it works no matter what. But if it's even length, it's sort of easier, I guess. Now, of course, it's a lot more simpler if it's a power of 2, the size of the array, because that way you can always break it in half evenly every single time. So, but it doesn't really have to be even or a power of 2 for merge sort to actually work. So that's basically sort of the essence of merge sort. So pretty much what we're going to do now is, so the idea of a merge sort is we're going to do merge many times. Now, how many times are we going to merge? Well, we'll find out later, I guess. Let's go ahead and first do an example of merge sort. But now we know how merge sort of works. Now we can actually try to run merge sort. So let's do an example array and just sort of trace out merge sort. It's actually a very simple algorithm to trace out. Probably the simplest out of all of the sorting algorithms we're going to do in this class. This one's definitely the simplest one to trace out. Let's go ahead and sort of begin. So I'm going to have maybe 3, 7, 10, 2, 8, 5, 13. So 1, 2, 3, 4, 5, 6, 7. Let's see here. Then I'll choose maybe 6. Then I'll have 11. Then I'll have 1. Yeah, 10 elements. So we want to go ahead and run merge sort on this array. Obviously, we can see here it's not sorted. So we're going to hope that merge sort is going to sort this correctly. So what does merge sort first do? Well, it's going to first break this list into two pieces. So right now we have a 10-element array. So we can break it into two arrays of size 5, the left half and the right half. So we're going to first do exactly that. So we're going to have our first half, so 3, 7, which I'll make it a little lower. 3, 7, 10, 2, and 8, 5, 13, 6, 11, and then 1. Let me go ahead and put these in blue. So you first have to break the list into two pieces. So for merge sort, I guess what you would do is you pass in the same array into both functions, but you pass in different indices, different endpoints, if you will. So for this example, from 0 to 9 is our array. So you first call merge sort, you pass in the same array, you pass in 0, 4, and then 5, 9. So you pass in the endpoints that sort of denotes that section of the array. So that's what you would do. But we'll just sort of stick to just this pictorial representation. Either way, though, we're doing the following. So what happens here is we're going to simply just break the list into two pieces and call merge sort on that left and that right side. So we have to first call merge sort on this subarray, this left side array, and of course we're going to have to get it sorted using merge sort. Once it's sorted, then we have to sort that right side, and then we have to merge them. But unfortunately, the left side is not sorted yet. Let's go ahead and sort it. So to sort the left side, well, we're going to have to call a merge sort on this smaller array. So what happens here? Well, you guessed it, we break this into two pieces once again. Now we have 5 elements in this situation, so to break this into two pieces, one sublist will have one more element. So we'll say that the left side will have only 2, right side will have 3. Or we could have the left side be 3 and the right side be 2. There's no, it's arbitrary, so I'll just have the left side contain 2 elements just because. So break this into two almost equal pieces, so 3, 7, 10, 2, and 8. Because we're doing the exact same code on this smaller array. I mean, that's what recursion is all about. We attack the same, we do the same exact work on either a smaller size list or a, for certain problems, like for the word ladder, it's really for a different instance. So we do the same exact work on different instance. Here, a different instance would imply a smaller array. So we do the same exact problem on a smaller array. So we have to sort this array using merge sort, which implies we have to first sort this array's left subarray, then the right subarray, and then merge them. But right now, however, well, this side is already sorted, but that's kind of by luck, really. Um, there's no guarantee that this will be sorted just like that. So anyway, we have to sort this array's left subarray, then the right, and merge them to get this top array to be fully sorted. So let's go ahead and continue with this. So you have to first break this left subarray into two pieces, 3 and 7. I'm using a different color pen this time, just to denote something different. So what happens here is now we have these two these two sort of subarrays, but they're both size 1. They're both one element, which implies that they're both sorted. So a size 1 array is sorted. So now we finally have a sorted array. So right now, for the array 3, 7, we broke it into two pieces and we sorted both pieces because they're both size 1, so they're definitely sorted. So now we can merge these two sorted arrays together. So to merge them, well, it's going to give us the result 3, 7. That's kind of a simple one, but that will be the result. So we have to use the red arrows mean we're going to merge. Blue means we're going to split the array and do merge sort. And then the red arrows coming together means we're merging two sorted arrays. So at this level right here, 3, 7, 10, 2, and 8, the left subarray is sorted, which is great. Now we have to sort the right subarray and merge that with this to get this whole entire array to be sorted. So we have to now call merge sort on this left side. So we're going to have 10 by itself, and then 2 and 8, like that. So once again, we have a size 1 array, which size 1 is sorted. And a size 2 array, well, in this case it's sorted, but there's no guarantee that it's sorted. The size 1 arrays, we can definitely guarantee that they're sorted. So now, for 10 to 8, the left side is sorted. Now we have to sort the right side. So we have to, again, call merge sort on that side. So we're going to have 2 and 8. They're both size 1 arrays in this situation. So they're both going to be sorted. So now we have to merge the list that contains 2 with 8. Let's merge these two lists, and we're going to, well, I guess we'll just get 2 and 8 is the result. So now, for the array 10, 2, and 8, the right side is sorted, the left side is sorted, so let's merge these two together. So we're going to get the result of 2, 8, and 10 if we merge these two arrays. So now we can see here for this array, the 3, 7, 10, 2, and 8, the left side is sorted, the right side is sorted by magic. Now we have to merge these two arrays, the 3, 7 array with the 2, 8, 10. Well, we can do that because merging is a pretty fast operation. So we'll have 2, 3, 7, 8, and 10. So now we can see here the left side. So let me go ahead and zoom out for a second so we can see the entire picture. So here we can see that the left side, we finally sorted it. So you see that all we had to do was break it in half until we have these size 1 lists, and we started merging them together. So actually, every time we have a red box, we return that back up to the previous function. But if I do that though, it'll be a very messy picture. But the red boxes mean returning back. We return back to the previous function call, and a sorted list is returned back. And we go ahead and merge that. So here, we had 3, 7, 10, 2, and 8. We called merge sort on the left side, right side, and eventually it returned back 3, 7 back to us. Then it returned back 2, 8, 10 up to us. And we go ahead and sort of merge these together and return that up to the topmost function. But I don't want to have us return like that. It would be too complicated. But essentially, at this top level, this array, the 3, 7, 10, 2, and 8, is officially sorted. So we have that part done. Now we have to sort this side. Once that's sorted, we merge that with this array 2, 3, 7, 8, 10, and then a whole list will be now sorted. So let's go ahead and just continue and just do this last step. So you have to sort the right side. Alrighty. So we're going to first break the list into two pieces. 5, 13, 6, 11, and 1. So we have to call merge sort on the two sublists once again. And then what will happen is magically, at some point, these two lists will be officially sorted, and we have to merge them. Now, right now, this is already sorted, but there's no guarantee a size 2 list could be sorted. Only a size 1 list is 100% guaranteed to be sorted. So what's going to happen now is we have to first sort the left side, which we have to, again, call merge sort on each half. So the following scenario, break this into two pieces again, but they will create these two size 1 lists, which will definitely be two sorted lists. So now we return a size 1 list back up and another size 1 list back up, and we're going to merge them to create a sorted list of size 2. In this case, it's a very simple example, but anyway, a 5 and 13. That'll be our 1 sorted list. So now at this level, we have the left side sorted. Now we have to sort the right side before we can merge that right side with this left side sorted list. So we're going to have 6 and then 11 and 1. We have these two lists we create. One is size 1. The other is size 2, which means we can't really assume that it's sorted. So in this case, the left side list is definitely sorted because I have one element 6. And then 11 and 1 is not sorted yet. We have to call merge sort on this list as well. So we're going to have 11 and then 1. We have these two lists. They'll both be size 1, which means that they're both sorted. And now we're going to merge these two lists together to create 1 and 11. So you merge these two. So now, for this array of size 3, 6, 11, and 1, the left side is sorted, the right side is sorted, so we have to merge them to make a larger sorted list. So we have 1, 6, and 11. So now, at this level, for this array, the left side is sorted, and the right side is now sorted. So we have to merge these two lists to create one bigger sorted list. So we're going to have, try to like zoom out a little bit here. So we're going to have 1, 5, 6, 11, and 13. If you just simply merge these two lists together. Like that. Let me zoom out here so we can see the entire picture. So this is going to be how this looks. So we can see here, we originally started off. So let me go ahead and let me just draw a blue box around this entire list as well. We initially called merge sort on this one big list at the very beginning. Like that. And we have this structure. So finally, we have the two sublists of our initial list. So at 3, 7, 10, 2, and 8, and then at 5, 13, 6, 11, 1, now there are finally two sorted sublists. Finally. So now we can merge those two sorted sublists together, because that's the whole idea of merge sort. Remember, we have our topmost list. We called merge sort on the left side and the right side, and we magically got two sorted sublists. Now we can merge them, and now we have one big sorted list. So if we merge these two lists together, we get 1, then 2, then 3, then 5, 6, 7, 8, 10, 11, and 13. If we merge these two lists together. And now we have one sorted list. So the red arrows really imply returning something. So we have these, so red boxes mean that we sort of have a sorted list, it gets returned back to the previous level, and then it's going to merge that with the other sorted list to create a larger and return those back up accordingly. But I drew it like this because otherwise it's a very conglomerated sort of picture. But really, that really is how merge sort works. So for the homework assignment on merge sort, I will definitely use a power of 2 because that way it breaks in half every single time because number 10 is not a power of 2. So what happens if we have these elements, we have to break the list into uneven sort of pieces. You have a 2 and a 3 list like that, which means maybe, let's say you decide to break it where it'll be 3 and then 2, not 2 and then 3. That'll be different pictures, so I don't want to really have to have the grader, work too hard on this. So to kind of make sure it's all good, we'll just make sure that I'm going to have a power of 2 used. So that way it breaks in half at every single level. So it's not going to have, it'll be easier to grade, I suppose. So that's really all. And it's a very simple code for merge. I'm not going to really write the code here. It's a very easy code. All we do is every merge sort function has sort of 3 lines, literally. Well, the first one is, so we always pass in the left and right endpoint of that sublist. So if it equals 1, if they're equal to each other, then we have size1 list return immediately. Otherwise, all we have to do is find the midpoint between L and R, and then just call merge sort on that first list, call merge on that second list, and then just call merge and pass in those 3 indices. It tells you what was the first sublist, the second sublist, and it'll just merge them together. It's 3 lines of code, and merge will be its own function, which is going to basically pass in the indices, endpoints of the left and right sublist, and then it'll just merge them into one. It's a very simple code, merge sort. So, but that's sort of the trace of how merge sort actually works. So, I guess any questions on that? Definitely seems to be the most simple. Very, very nice visual representation of how merge sort looks like. It does look nice. I don't know, something about the whole tree structure looks kind of nice, I guess. So I do like how it looks. So anyway, okay, good. We have somebody who agrees. All right. So, all right. So let's go ahead and now go into the runtime analysis because, of course, we have to, we can't just, of course, we can trace out these algorithms. We have to, of course, know the runtime. It's always important to know, is this really better than what we've done so far? So let's go over time, complexity, analysis. You always have to do that. So the idea is we have to run this merge operation, which is a linear time sort of algorithm, many times. And the question is, well, how many times do we have to run merge? Well, let's go ahead and draw another sort of picture again. But this time I'm going to sort of, it'll always break in half every single time. Let's just do sort of a simple example here. So we're going to sort of break it into 2 pieces as well. So let's just sort of look at a generic sort of example of merge sort. So let's try and we do a few more of these. So let's suppose we break it in half every single time, just so we can very easily analyze its runtime. And eventually we're going to have these size1 lists at the end are going to be the result. So what happens is we return all of these back up sort of to the parent function. And then it's going to merge these and return them up to their parent function. These two get merged, return them back to the parent function, and then it will merge those last 2 lists together, and that's is kind of really the more sort of the real way it works. It returns up this function sort of recursive function sort of tree, and it will always merge those 2 sorted lists together. So every level, we're going to have to do a merge operation. So we're going to have to do merge over here on all these lists, merge on all of these, and then do a final merge at the very end. Now each merge will take O of n time, as we already sort of stated earlier. So collectively, because, okay, you may wonder, well, these lists are all kind of small. This list is not really n. However, if we add up all the work done at this level, collectively, it's going to be linear, O of n, if you collectively add up all the steps that every merge operation does. Same idea above. If we merge this with this, collectively, it's going to be also n. So the idea is that every single level, it'll be n. And then the question is, well, how many levels do we have? Well, we have to divide the list in half every single time until we hit 1 or 0. And there's a very nice sort of function that models that behavior perfectly. if you guessed logarithmic, you'd be correct. So it's going to be log 2n number of levels. And each level, we do a merge operation O of n. So there's your answer. Let's go ahead and write this out. So we break the list into two pieces at each level, two pieces of size. Okay, so break the list into, darn it, I guess I messed up this. So break the list in half, basically. So we have these two lists of both size n over 2 every single time. So this sort of behavior we're going to have exactly. So we will have log base 2n amount of levels. And each level requires a merge operation that takes O of n time. So O of n times log 2 of n. So thus, merge sort runs in O of n log n time. So that's merge sort. So applying divide and conquer, we get a better runtime than insertion sort. So for merge sort, there is no case where it could be better or worse. It'll actually be n log n every single input scenario. There's no input that can cause merge sort to get worse than n log n or even better than n log n. It'll always be n log n every single time. So very simple to remember because we're doing these merge operations, which are O of n runtime, and we're doing that log n number of times. So O of n log n. So that's one of our simpler algorithms, merge sort, and we see it has a better runtime. Now, just to sort of, how should I say, just to kind of reiterate this. So we always consider n to be very large. So if let's say we have a 5-element array or 10-element array, then merge sort is an overkill compared to using insertion sort. It's like taking the highway to go somewhere across the street. Highway, it's very fast. If you don't have to go very far, there's no point taking the highway. So merge sort is faster, but really we have to have a big enough n to really see a real difference between merge sort over insertion sort. But typically for algorithms, we have to always consider that our input will always be very large. Otherwise, there's no point to really study algorithms, and I guess computer science is obsolete then because if there's small input sizes, we can just easily sort or perform any kind of work on input using sort of a very naive approach because it wouldn't matter if we do it in a naive way because it'll be good enough. But we always have to consider big input sizes. We want to have a computer sort of process the input quickly, and having a better algorithm will make a big difference. So there's that. Merge sort. Very simple sorting algorithm. And now we'll have our more challenging algorithm for sorting. This is going to be Quicksort. Let's go over Quicksort next since we do have about a half hour or so, or not quite a half hour, but almost a half hour. Let's go over the last one, Quicksort. And as the name suggests, Quicksort should be pretty quick because otherwise it wouldn't be called Quicksort. So anyway, once again, Quicksort is also a divide and conquer algorithm. And divide and conquer, for many problems, seems to always give us a good runtime. So we don't really cover too much divide and conquer in this class, but in a 400 level class, depending on who you have it with, you cover other nifty divide and conquer problems where we take a simple problem and we sort of find a way to break it into small components and we get a better runtime than the brute, straightforward way that you've always used for common sort of problems, I suppose. But anyway, this will be our other divide and conquer. And in fact, also, before I move ahead, binary search is also divide and conquer algorithms. I'll maybe on a study guide I'll put those on there. But binary search though also it divides the problem. It breaks lists into half and then it attacks either one side or the other side for binary search. That's also divide and conquer algorithm. But that one is kind of not as interesting as merge sort or I guess quicksort. So how does quicksort work? Well, we first have to choose a pivot. Choose a pivot. And a pivot really is any element in the array. So any element in the array. So we pick some value in the array and we're going to designate this element as our pivot. And then what's going to happen is we're going to partition the list. And I'll go over the partition in more detail in a second, but we're going to partition the list. So what partition does is you're going to sort of, I guess you can say, arrange the list where one side contains all the elements less than the pivot, and another side that contains all the elements larger than the pivot. Now, once again, you could say, well, one side could contain elements less than or equal to the pivot, and the other side is strictly larger, or you can have it where one side contains less than the pivot, other side contains greater than or equal to the pivot. It's arbitrary, but we'll assume for now we won't have duplicates in our list, so we can make this claim. But that's all we're going to have to do. We have to partition the list like this. So we pick our pivot, and we have to arrange our list in such a way where the left side will contain everything less than the pivot, and the right side will contain all the elements larger than the pivot. Once we do that, we essentially broke the list into two pieces. So then, you guessed it, we have to call quicksort on each piece, I guess recursively is the idea. Then what happens is, once again, magically, it will sort those two lists. And once that happens, we have one big list because we have everything that's less than the pivot will get sorted. Then the pivot, everything larger than the pivot is also going to be sorted. So we'll have one sorted list. So very similar to merge sort. Except for merge sort, we first have to break the list in half and merge. Here we first have to partition the list into two pieces. Once we have that, quick sort one side and the other side, and we have one sorted array. So the real bulk of quicksort, just like with merge sort, is that partition part takes more time. That's really the whole essence of quicksort is partition. Let's go over partition right now. So partition It'll be a function. It'll take in some array, I suppose. It'll take in this L and R. I think that's all it takes in. Yeah. So we want to have the array passed in, and we want to know the left endpoint and right endpoint because we're going to call partition many times again, just like with the merge operation for merge sort. So we have to basically know what part of the array we're going to perform partition on. So initially, when we first call partition, we're going to pass in 0 and n minus 1, where n is the size of the array. So we're going to call partition on the entire list. And as we call partitions more often, we're going to pass in different L and R values so partition knows what part of the array it's going to perform this partition on. So the first step is we're going to just choose a pivot. So what will happen once I pick a pivot, so let's see, to the pivot at index, let's say index, let's say R. Why did I say R? I'm going to say index A. Sure, that's where pivot will be. So what I always do is I always swap array at index L with array index sort of A where the pivot is. So the way I was taught Quicksort is I like to always have the pivot somewhere out of the way, not really getting involved in this whole partitioning sort of phase. So you put the pivot to leftmost position. And okay, and now we're going to create two indices. So we're going to create sort of index I and j. So I initially is set to L plus 1. And then j is initially set to R. So we're going to assign, so j equals R, I equals L plus 1. And then we now perform the actual loop that's going to run this partition. So what's going to happen is in our loop, what's going to happen is if the array at index I is less than our pivot value, which is the element at index L, then increment I by 1. And then of course if, just do this like this, so if array index j is larger than a pivot, then j minus minus. Now we'll assume for right now there's no duplicates in our array. If there were, then either we have to either do this or we have to do this. But for now, we'll just go ahead and just keep it simple. We'll have our elements all be distinct, so there's no chance we can have any equals, but we have to sort of designate one side to be less than equal to other side larger or vice versa. Now, we have the situations, what if, so if we have the case where array index I is larger than the pivot, and array at index j is less than a pivot, then we have this sort of deadlock. We can't move I and j. So to break this deadlock, we're going to swap array index I with array index j, and then we're going to set I plus plus and then j minus minus, because now we swap those two items, so now the i's and j's can safely move. And then we're going to do this loop. So we're going to, I'm going to go ahead and just sort of, so we're going to, so as long as, so once I and j cross, then stop the loop. So this is going to be a loop of some sort. So once this last condition right here is, once this is correct, once this is true, that means we're going to stop looping. That means we successfully partitioned the list into two pieces. Because as the i's are moving, we're sort of creating a list to the left of I that's constantly going to contain elements less than a pivot, and the j is moving, so I guess we can look at it like this, actually. So here's the best way to think about this image. So we have the following array like this, and we have our L index and our R index, and a pivot will also be here as well. Pivot's always to the left. And what's happening is, I'm going to use blue for I and red for J. So we're setting, let's say I is over here, then all these elements here are less than a pivot. And if J is over here, everything is larger. And as we move the I over, as we're moving I and moving J, this list gets bigger and bigger. And these elements are all going to be, so the blue elements will denote less than a pivot, and the red denotes larger. So actually, this should also be involved as well. Like that. Now a pivot is sort of out of the way. The pivot is sort of sitting back and not getting involved in this. So think of like I and J as like from that West Side Story. They're going to come together. The pivot is sitting out there and doesn't want any part of this really. So at some point, the I's and the J's will cross sooner or later, because this loop will ensure that I and J is definitely going to move. And at some point, what's going to happen is I will be here, and then the J is going to be here at some point. And that implies that all these elements right here are going to be less. So everything to the left of I is less. Everything to the right of J is going to be larger. So in this case over here, well, actually this is a kind of weird picture, but essentially, yes. So we can think of it as like this. So J is like, so you could actually do that. You could just set pivot just to L and just like that. But if you want to pick a different pivot potentially, let's say you didn't want to use that leftmost element as your pivot, you have to pick a pivot somewhere in the array and then swap it to the front if you did not want to use that leftmost element as your pivot. So this way you have the choice of picking any value as your pivot. So what happens is, at this point, we have the following scenario where this will be your I index right here. This will be your J. They cross over at some point. So the element index I actually is going to be, this element is going to be larger as well. So this element J is going, so let me just answer this question first before I move on. No, we don't want the smallest number to be the pivot. We'll see why. We don't want the smallest. Although it would still work, we just don't want that. So, but we'll get there. We'll get the analysis part of Quicksort later. So at some point, once the i's and the j's cross, then everything to the left of I is smaller, everything to the right of j is larger. So then, at this point, now we broke this list into two pieces. So now we can definitely swap the pivot with whatever is in index j. So I'll write this note over here. Swap the pivot with the element at index j. So we know that element index j has to be less than the pivot because everything to the left of I is smaller. So wherever j is, it has to be smaller than the pivot. So we swap these two elements, then what's going to be the result? Well, we'll have the following array. I'll draw this out again. The pivot will be right here. And then we have the following scenario. Because, let me just zoom out so we can see all of this. Because element j was a blue element. Because, let me just see if I can move this down a little nicer. Okay, so because j was on the left of I, that j element had to be smaller than the pivot because everything to the left of I is going to be smaller than the pivot. So swapping j with p, or just pivot value, it's going to still take a blue element and put it to the front. So at this point here, we partition the list among the pivot, where now we have these two sublists, the blue list and the red, or in this case, the blue really means that its elements less than the pivot, and the red means larger than the pivot. So now, and a pivot is now in its correct final position. So the pivot never has to move because why should it? Everything to the right is larger and the left is smaller, so the pivot is right there fixed in that position. It will never move ever again. And now we simply have to call Quicksort on each sublist. It's going to also do that whole partitioning sort of work, but the end result is the left side will get sorted, the pivot is in the correct position, the right side will get sorted, which means you will have one sorted array. Because of course, recursion is magic. That left side will get magically sorted by Quicksort. Then the right side will get magically sorted as well, and that pivot is in its correct final position, so you will have one sorted array at the end. So that basically is Quicksort. So I guess that's sort of just the pseudo-ish code, or kind of a representation pictorially of how we do this. So we'll go over the analysis part later on, but let's go ahead for right now. I have maybe a few minutes left. Let's go over and just sort of begin an example on Quicksort. And now I probably won't finish the example right now, but I definitely can continue it next time because OneNote kind of saves the work, so I'll have to remember it. I know exactly where we left off. So let's go ahead and start the example, and I'll finish it off next time, obviously, and I'll go over analysis of Quicksort, the runtime. But let's go ahead and just do an example for now. So I'm going to pick, let's say, an array. So I'm going to have maybe 5, 2, 4. Let me see. I'm going to pick, let's say, 10, 7, 8. Then I'll pick, let's see, I'll pick 6 over here. Then I'll pick 1. Actually, I'll pick 6, 1, 2. And let me see, what am I not missing? 7, 8, 9. And I'm going to pick maybe, let's say 13. Yeah, good enough. So now typically for whenever we trace Quicksort, so for the grader's point of view, so I'm going to fix this because it's a little bit kind of a little weird. I'm going to just kind of even this out a little bit just because it looks a little better now. So any element can be the pivot, but when you trace out Quicksort on paper, we'll just always pick the left element as your pivot, just so that way everybody's sort of trace of Quicksort will be the same, so it's easier for the grader to actually sort of grade the assignment. So right now, I'm going to pick this as my pivot, and of course this will be L, and this right there is going to be R. So my pivot is chosen, and then I will be the element after the pivot, and then J will be at index R. So now we can go ahead and begin. So I'll do this one example, and this I'll do this one portion here, then I'll go ahead and I'll stop. So anyway, let's go ahead and proceed. So first check. So I and J hasn't crossed, so we have to run this partition loop. We're not done with it. We check to see, well, the element at index I is less than the pivot, so we're going to move I by one element over to the right. Then J element contains 10. It's larger than the pivot, so move the J over by 1 to the right. And once again, we proceed. So I and J's haven't crossed yet, so we have to still run this loop. So we check. The element at index I is less than the pivot again, so we're going to go ahead and move I over by 1. And then J element is in fact larger than the pivot, so move it over by 1 as well. Now in this situation right here, I can't move because the I element is bigger than a pivot, so I can't move, but the J index actually can move because J contains a value 8 bigger than a pivot, so J can move. So, okay, fine. As long as one of these two can move, we're good. But now we have an issue because right here, I can't move and J can't move either because I is pointing to an element that's larger than the pivot, and J is referring to element 2, which is less than the pivot, so we can't move. So in this situation, to break this deadlock, we're going to swap these two values. So let's go ahead, I'm going to redraw the list over here so it doesn't get too conglomerated. So 5, we have our L, we have our pivot still over there. We have 2, 4. Oh, I have duplicate values in my list, darn. Okay, you know what, I have an idea. I'm going to just use 0 then for this. My mistake. 0 is good enough. 0, 4, then we'll have 2, 1, 13, 6, 8, 7, and 10. Then we have our R, and I was pointing here, and J was over there. So we swap these two elements. So now we can safely move I and J accordingly. And then right here, again, I can move by 1 because I is definitely smaller than the pivot. So I moves, and J also can move because element 13 is bigger. So now we see here we crossed. I and J finally met somewhere. And that's where they're going to do battle, I guess, if according to West Side Story or the modern day rendition of West Side Story, Hey Arnold. So we're going to have them, the two sides cross. And now we partition the list into two pieces. So now the J element, we simply swap it with the pivot. And then let's represent this array. So we're going to redraw this. We're going to have the 1 over here. 1, 0, 4, 2, and 5. And I'll box this in. 13, 6, 8, 7, and 10. And now 5 is in its correct position. So we're good there. And everything to the left of 5 is smaller. Everything to the right of 5 is larger. So now we can go ahead and quicksort the two sides independently, and we will have one sorted array. So we're going to resume this example next time and go over analysis. So for right now, I guess that's it for today. So take care, you guys. Thanks for watching. Stay safe. Have an awesome rest of your day, and I'll see you guys on Wednesday.